Hi, my name is Struan and I'm a scientist at Izon Scientist, and today I'll be explaining what happens when you change the tunable parameters of your Exoid and how they affect your measurement. The three controllable parameters on the Exoid are the voltage, stretch, and pressure. These interact with your sample particles in different ways to affect the quality of your measurement. Understanding how each of these system parameters influences your measurement will help you improve the quality of your data. Once your nanopore is set up and a voltage is applied, a current will flow through the nanopore from one electrode to the other, resulting in a baseline current. When no voltage is being applied, the baseline current will be zero. When a voltage is applied, the magnitude of this baseline current is dependent on the size of the nanopore aperture. The smaller the nanopore, the fewer ions can flow through the nanopore, and therefore the current will be lower. Voltage, together with stretch, can be used to control the baseline current, as well as your blockade magnitude. Controlling your blockade magnitude is particularly important for situations where you may be losing some of your blockades in the baseline noise. To alleviate this challenge, you can increase your signal-to-noise ratio by increasing your blockade size. To do this, you can change the stretch from 47mm to 45mm. As you can see, the baseline current drops from 127 nanoamps to 83 nanoamps. To return to the previous baseline of approximately 127 nanoamps, we must now increase the voltage to achieve the same level of current through the reduced size of the aperture. By increasing the voltage to 600 millivolts, we return the baseline to 125 nanoamps. Because blockades are a measure of the volume of electrolyte displaced relative to the total amount of electrolyte in the nanopore, and the total volume of electrolyte in the nanopore has now decreased while the sample particles are the same size, you can see the blockades that were about 0.1 nanoamps in size are now closer to 0.2 nanoamps on average, reducing the likelihood of losing particles in the noise. Now, if we reduce the stretch even further to 44mm, the current drops as the nanopore contracts, and by changing the voltage to 800 millivolts, we return the current to 127 nanoamps. And you can see the same blockades are now on average 0.3 nanoamps in size. Every nanopore is unique, so the magnitude of this change as you stretch or de-stretch the nanopore will vary. But in general, you should be able to resolve smaller particles better when your signal-to-noise ratio is increased. There is a chance that at lower stretches, your nanopore may be more prone to blocking. The other tunable parameter is the pressure. The Exoid can apply either a positive or negative pressure to the upper fluid cell to control the speed at which samples flow through the nanopore. While applying more positive pressure increases the speed of the measurement by driving particles through the nanopore more quickly, a trade-off is that this decreases the average blockade size, as the sample particles spend less time being measured inside the nanopore sensing zone. By increasing the pressure from 100 pascals to 800 pascals, the rate of particles nearly doubles from 400 to 800, but the size of the blockades decreases by about 0.1 nanoamps. Increasing further to 1500 pascals causes the blockade rate to skyrocket to 1800 particles per minute, and the blockade size gets even smaller, averaging about 0.15 nanoamps in size. Tuning your parameters so that measurements are performed using a baseline current and particle rate within the recommended range while maximizing the size of your particle blockades will allow you to get the most out of your Exoid. Please visit us at support.izon.com for more information or if you have any questions.